Hey everybody, it's Monday, April 26th, and the goal for this video here is just to very briefly review some of the most incorrectly answered questions on the assignment that was entitled AP Physics Multiple Choice Review Day Number 1. Now, the good news, at least we can start out by talking about, the good news is that the average on this assignment was 5 out of 8 questions correct. And for the purposes of the AP exam, considering that that's about 62.5% correct, that's about a 4, which is pretty good for the AP test for sure. Having said that, there were a few questions, specifically these few in the middle, or at least on my list here, these few in the middle, that large numbers of people got wrong. And so I want to go ahead and discuss those now. The first question is the question that says, explain the gain in speed of Mars as it orbits. Now, I left it here in the slide as EXPLAN because that's what it says on AP Classroom, so you can go ahead and find it. Now, as the page will show, which we'll go back to in a second here, the correct answer is A. And while the vast majority of you picked A, there were 2 people who picked each of the wrong answer choices. And because 6 out of the 23 people who did it is over a quarter of the class, I wanted to just make sure we get a moment to discuss this. Now, today's free response question is all about orbits. And so this would probably be a pretty good idea for us to revisit concepts associated with an orbit. Now, a key thing to remember about objects in orbit is that there are 3 ways that you can explain orbits. You can talk about forces, you can talk about energy, and you can talk about angular momentum. Now, as you'll notice here, there are a couple of explanations using all of these different methods, and really only one of them is right. So A is correct because it says, as Mars gets closer to the sun, the Mars-Sun system loses potential energy and Mars gains kinetic energy. So notice this is talking about like a basic conservation of energy scheme. Now, it is true for like planetary systems that the best way to describe conservation of energy is this equation. You don't have to think of it this way because this way is a little confusing. Remember, this equation shows the gravitational potential energy looks like it's inversely proportional to R. And so what that kind of makes it seem like is that as the R gets bigger, as the object gets further and further away, the gravitational potential energy gets less. Now, of course, that's not true. And it's important for everybody to remember this equation will always show you as the objects get farther away or as that quote unquote height increases, the gravitational potential energy is going to get bigger. You have to remember for this equation, it's a little confusing because the number is negative. As R gets bigger, this whole number is going to get smaller, but you have to remember it's going to be a smaller and smaller negative number. And so since it's becoming a smaller and smaller negative number, it's actually technically getting bigger. And so when Mars gets farther away from the sun, the potential energy gets bigger. And when it gets closer, the potential energy gets smaller. And of course, we have to ask the question, well, what happens to that potential energy? It turns into kinetic energy. Let's just very quickly go through the wrong answer choices. B says a component of the gravitational force exerted on Mars is perpendicular to the direction of motion, causing an acceleration and hence a gain in speed along that direction. I'll be honest, when I was looking over this question, deciding to assign it, I wasn't really sure what was wrong with that the first time I read it. Then I skipped it and came back and I said a component of the gravitational force is perpendicular. Oh, it's all about it being perpendicular. An acceleration that causes a gain in speed has to be in the direction of the velocity. Circular motion really tells us why B is wrong, because remember, if an object has a speed and then has an acceleration that is perpendicular to that, that actually does not cause a gain in speed in that direction. When the acceleration is perpendicular to the velocity, the only thing that happens is the velocity changes direction. The only way an object can gain speed is if the acceleration is parallel to the velocity or has a component that's parallel to the velocity. So that's why that one is wrong, because perpendicular acceleration will not cause a speed change. For C, it says the torque exerted on Mars by the sun during this segment of the orbit increases Mars-Sun system's angular momentum. This is a really important thing to remember. If we draw the position vector for the Mars-Sun system, it goes from the pivot point, which is the sun, to the point where the force is applied. That would be this red arrow R. And then if we were to draw the force, which I'll draw in blue, the force goes from Mars toward the sun. It's very important to remember the torque due to gravity. So notice I'm writing FG as a subscript. The torque due to gravity is 0. Gravity does not exert a torque. That's why the angular momentum of Mars is conserved. It's also important to remember when we're talking about an orbit and we're talking about the angular momentum being conserved, we're not talking about the Mars-Sun system. We're only talking about Mars. And that's because Mars has no external torque exerted on it. And so the equation would just be mRV equals mRV, where we put a 1 and a 1 on the R and the V here first, and then we'll put a 2 and a 2 here. And basically what we're saying is when the R gets smaller, the V is going to get bigger. That's it. The reason why Mars speeds up in the context of angular momentum conservation is because its rotational inertia gets smaller when it gets closer to the sun. Its mass is getting concentrated closer to the pivot point. And so because its rotational inertia is getting smaller, its angular velocity and thus its linear velocity, right, because V is equal to R omega, the angular velocity and the linear velocity increase. For D, it says the centripetal force exerted on Mars is greater than the gravitational force during this segment of the orbit, causing Mars to gain speed as it gets closer to the sun. Remember, the main forces analysis that you have to use for orbits is that the centripetal force is the gravitational force. So the centripetal force can't be greater than the gravitational force. The centripetal force is the gravitational force. If we wanted to explain this in the context of just forces, we would say a component of the gravitational force exerted on Mars from all the way over here on the outside of its orbit is in the direction of its velocity as it swings around here. And because the force is in the direction of the velocity, it accelerates and thus gains speed. But that's because the centripetal force is the gravitational force, not because the centripetal force is bigger. And so that's why the answer here is choice A. All right, moving on to the next question here. This question says acceleration of a block projected up ramp, and it says a block is projected up a frictionless plane with an initial speed v naught. The plane is inclined 30 degrees above the horizontal. What is the approximate acceleration of the block at the instant it reaches the highest point on the inclined plane? I kind of have a feeling that this question asking about the acceleration at the maximum height is going to have a bunch of people answering 0. Not a ton, but a good amount of people who got this wrong. Now, other people said 10 meters per second squared down the incline, and one person said it cannot be calculated without knowing the value of V naught. All right, so let's take a second to talk about this. Now, notice here they said this is a frictionless inclined plane. So that means when this object is at its maximum height, it has 2 forces acting on it. It has the force of gravity coming straight down, and it has the normal force. Now, notice I said 3 forces because I was thinking about friction, but again, it says it's frictionless, so that doesn't act. That means, now here's the deal, because it has only 2 forces acting on it, gravity and the normal force, that means the only force acting down the incline is FGX. And FGX, we're saying, is equal to the net force on this block. That should make sense to everybody. The normal force is being canceled out by FGY. That means the only thing that's not being canceled out, and thus the net force, is FGX. So it's important to realize here what we're saying is FGX is given by the equation mg sine theta. So watch how we get the answer here. The first thing we should say is Fnet, which is equal to FGX, is going to be equal to mg sine theta. But of course, we're not solving for the net force. We're solving for the acceleration. So we'll say mass times acceleration equals mg sine theta. That means the acceleration of the object we can get by solving this for A, and notice that's pretty easy because the m's cancel. That means the acceleration of an object on a frictionless inclined plane is g sine theta. And what that tells us is, in this particular instance, the acceleration is g, which is about 10, times the sine of 30. And since the sine of 30 degrees is a number you should know, It's a half. That means the answer here is B. Now, I do think it should be noted, especially for those of you who picked the answers that have the 10 in it, the acceleration due to gravity is 10. When an object is on an inclined plane, then, the acceleration has to be 10. Because now, instead of just having the gravitational force acting down on the object, you have the normal force opposing the gravitational force a little bit. It cancels out FGY. The acceleration down an inclined plane, even if there's no friction, always has to be less than 10. And if you realize that you don't need to know V0 to calculate the acceleration because the inclined plane is a forces problem, and you knew that it wasn't going to be 0, then the answer could automatically be determined to be B without doing a calculation. Because it's got to be less than 10 and bigger than 0, and that's the only answer choice that works is 5. All right, moving on. The next question here, which is the question that I think the most people got wrong, says force exerted on the roller coaster at the top of the loop. It says you got a 100-kilogram cart going around the inside of a vertical loop of a roller coaster. The radius of the loop is 3 meters, and the cart moves at a speed of 6 meters per second at the top. The force exerted by the track on the cart at the top of the loop is, and you got 200, 800, 1,000, 1,200, or 2,200 newtons. Now, I'm sure the answer spread may be all over the place here. Force exerted at the top of the loop. The answer here is 200, and we kind of have answers all over the place. Most people said the answer is 1,200. So let's go ahead and take a look at this here. It's important to remember we did a lot of these questions in the uniform circular motion unit. The roller coaster loop-de-loop was one that confused a lot of you, though, because a lot of you seem to think that the normal force goes up. The surface here, though, is upside down. So the normal force goes down, and so does the force of gravity. And since the question here is asking you about the force exerted by the track, they're asking you for the normal force. And so we know here the mass of the cart is 100 kilograms. We know the radius is 3 meters. We know the speed at the top, it says, is 6 meters per second. And we know G here, of course, is 9.8 meters per second squared. And so because both of these forces are going towards the center of the circle, we have a pretty easy time. Because remember, we said the free body diagram circular motion problem says you draw your diagram and then you take FC and you set it equal to the forces going toward the center of the circle minus the forces going in the opposite direction of the center of the circle. And notice here there are no forces going opposite the center of the circle. So we have here Fn, the normal force, is equal to Fc minus Fg. So that means the normal force here is going to be mv squared over r minus mg. And so we have the normal force is going to be, I'm going to actually just factor out the m. So I have v squared over r minus g. And so plugging in my numbers here, I've got my mass, 100 kilograms, and then I'm multiplying that by v squared, so that's 6 meters per second, whole thing squared, over the radius of the loop, 3 meters in the denominator here, and then I've got minus g, which of course is 9.8 meters per second squared. Now, of course, 6 squared is 36, and 36 divided by 3, so notice here 6 squared is 36, 36 divided by 3 is 12. Then when I subtract 9.8, I get 2.2. And of course, when I take 2.2 and I multiply it by 100, I'm going to get here 220. And so notice here, because they made these answers so different, 200, 800, 1,000, 1,200, 2,200, it's not surprising that the answer is A. Now, of course, why does the answer A say 200 and not 800? Well, there are two arguments you can make. The first argument you can make is, well, all these numbers are given to 1 sig fig. So the answer is going to be given to 1 sig fig, but it's going to say on the top of the multiple choice section of the test, if you want to estimate G as 10, you can do that. And so notice if we take 6 squared, 36 over 3 to get 12, and then subtract 10, inside these parentheses here, we would get 2. And 2 times 100 is 200. When the answers are that different, you can estimate G as 10, because close enough is good enough. All right, and that brings us to the last question here I wanted to talk about. I was going to do that work on the blank slide. I had enough room there. It says the toy car shown in the figure above enters the vertical circular loop with an initial velocity and moves completely around the loop without friction. If the car has no means of self-propulsion, which of the following is true of the car's acceleration at the instant it is at point P? Now, the fact that it says if the car has no means of self-propulsion means it's not going to be exerting any additional forces as it goes around to give it an additional acceleration in the upward direction. It cannot propel itself. This thing has an acceleration for two reasons. It has an acceleration, towards the center of the circle, because it's a circle, and thus it has a centripetal acceleration. And it also has an acceleration that points straight down. That means the answer here should be D. Now, I'm assuming there's a pretty good spread on these answers as well. There were 10 people who got this one wrong, and almost everybody picked it is directly towards the center of the circle. It's not a ridiculous answer, I think, but it's important to realize in that instance, you're forgetting about gravity. It has to have a part that is both directly towards the center of the circle and downward to account for the centripetal force, or which is really the normal force from the track here, and the gravitational force. And so the answer is D. Now, I notice here one person picked E. It has components both downward and away from the center of the circle. Of course, centripetal force points toward the center of the circle. Those are the questions that large numbers of people got wrong. Now, it should be noted, some of you got other questions wrong. If you have any questions about these, please reach out via email and let me know. But with that, that is it for this short little video reviewing these problems. Have a good one, everybody.